Look down at your arm right now. Go ahead, really look at it. What do you see? Smooth skin. Maybe a few fine hairs, barely visible unless you're in bright light. Now picture a chimpanzee's arm. Thick dark fur covering every inch. Or a gorilla, a bonobo, an orangutan. Every single one of our closest living relatives is covered head to toe in a dense coat of hair. But us? We're naked. Bizarrely, strangely, inexplicably naked. This is one of the greatest mysteries in human evolution, and almost nobody talks about it. We walk around every day in these hairless bodies, and we just accept it as normal. But it's not normal, not even close. Out of roughly 5,000 species of mammals on Earth, humans are the only ones that lost almost all their body hair. We're biological freaks. Naked apes wandering around a planet where basically every other creature our size is covered in fur or hair for very good reasons. Here's what makes it even weirder. We didn't just lose our hair. We kept it in the strangest places. Think about it. We've got thick hair on our heads, hair in our armpits, hair around our genitals. Men grow beards, but our backs, our chests, our arms, our legs, the vast majority of our body surface is completely exposed, and we have more hair follicles per square inch than chimpanzees do. The follicles are there. They're just producing tiny, nearly invisible hairs instead of thick, protective fur. Something happened in our evolutionary past that flipped a genetic switch and turned us from hairy apes into naked apes. But what? And more importantly, why? Hair is incredibly useful. It protects you from the sun. It keeps you warm at night. It cushions your skin from scratches and insect bites. It helps regulate body temperature. Every other primate on Earth has kept their fur for excellent evolutionary reasons. So why did we lose ours? Scientists have been arguing about this question for over a century. Charles Darwin himself was puzzled by human hairlessness. He proposed that maybe we lost our hair because our ancestors found smooth skin more attractive. Sexual selection, he called it. But that explanation always felt incomplete. Because sure, maybe humans started preferring less hairy mates, but that doesn't explain why hairlessness would have been advantageous enough to spread through the entire species. If you're using this to fall asleep, that's exactly why I make these videos. So maybe subscribe and tell me where you are and what time it is. I check the comments and it's wild. Tokyo at dawn, London at lunch, Los Angeles at lights out, all watching at once. The thing is, losing our hair should have killed us. Our ancestors lived in Africa, where the sun is intense and dangerous, where nighttime temperatures can drop dramatically, where thorns and biting insects are everywhere. Going naked in that environment sounds like evolutionary suicide. Yet somehow, not only did our ancestors survive hairlessness, they thrived because of it. We spread across the entire planet. We became the most successful large mammal in Earth's history. And we did it in these weird, exposed, vulnerable, naked bodies. The story of how we became naked apes isn't just about hair loss. It's about a series of dramatic transformations that rewired our bodies from the inside out, changes to our sweat glands, modifications to our skin, alterations in how we regulate temperature, the evolution of our brains and our ability to create tools and clothing, and possibly, just possibly, changes in how we saw each other, how we communicated, how we formed social bonds. Some scientists think we lost our hair when we left the forest for the open savanna. Others believe we went through an aquatic phase in our evolution, living partly in water like seals or dolphins. There's a theory that we shed our fur to get rid of parasites and disease-carrying insects. Another idea suggests our hairlessness was all about cooling, about developing the most sophisticated temperature regulation system of any mammal on Earth. The truth is probably more complex than any single explanation. Evolution rarely works in straight lines. Our naked skin likely resulted from multiple pressures pushing our ancestors in the same direction over millions of years. Each theory explains part of the puzzle. None explains everything. But when you put them all together, a fascinating picture emerges of how and why humans became the naked apes we are today. Over the next few hours, we're going to explore every major theory about human hairlessness. We'll travel back millions of years to meet our hairy ancestors. We'll walk through changing landscapes as forests gave way to grasslands. We'll dive into controversial ideas about water-dwelling human ancestors. We'll examine the microscopic world of parasites and pathogens. We'll discover how our unique sweating ability changed everything. And we'll explore the cultural evolution that made nakedness not just possible, but advantageous. By the end, you'll never look at your own smooth skin the same way again. Because this isn't just a story about hair, it's the story of how humans became human. So let's go back, way, way back. Back when our ancestors were still covered in fur, living in trees, and had no idea that their distant descendants would one day conquer the world in these strange, naked bodies. Let's rewind the clock, way back. Not thousands of years, not hundreds of thousands. We're going back 6 to 7 million years ago, to the humid forests and woodlands of Africa. Picture this landscape. Dense canopies overhead filtering the sunlight into scattered patches, trees everywhere, creating a three-dimensional world where safety meant staying off the ground. And in those trees, moving cautiously through the branches, were your earliest ancestors. They didn't look like you, not even close. These early hominids, the very first members of the human family tree after we split from our chimpanzee, cousins, were covered head to toe in thick body hair. Not just a light fuzz. We're talking dense, protective fur similar to what you'd see on a modern chimpanzee or gorilla. Every square inch of their bodies except their palms, soles, and parts of their faces was carpeted with hair follicles producing sturdy protective covering. And here's the thing, this wasn't some evolutionary accident. That body hair was absolutely essential for survival. It was literally keeping them alive every single day. Let's start with temperature regulation. Counterintuitive as it sounds, body hair doesn't just keep you warm. In the right configuration, it's actually one of the most sophisticated climate control systems in nature. Those dense hair coats created an insulating layer that trapped air against the skin. During cool nights in the African highlands, this kept body heat from radiating away too quickly. During hot days, the same hair coat provided shade for the skin underneath, preventing overheating. Modern chimps demonstrate this perfectly. They can live in environments ranging from humid rainforests to relatively dry woodlands, and their hair helps them maintain stable body temperature across all these conditions. Your ancestors 7 million years ago had the same advantage. That coat of fur was like wearing a built-in climate control system that automatically adjusted based on the environment. But temperature regulation was just the beginning. That body hair provided critical protection from ultraviolet radiation. The African sun isn't forgiving. UV exposure at equatorial latitudes is intense enough to cause serious tissue damage, increase cancer risk, and break down folate, a vitamin essential for reproduction and fetal development. Body hair acted as a physical barrier, scattering and absorbing UV radiation before it could penetrate to the vulnerable skin below. Every hair shaft was essentially a tiny UV shield, and when you had millions of them covering your body, the protection was substantial. Then there's the mechanical protection factor. If you've spent any time in forests, you know they're not gentle environments. Thorns, sharp branches, biting insects, parasites, minor abrasions from tree bark, all of these are constant threats. Body hair provided a cushioning layer between the skin and the hostile environment. It wasn't armor, but it was enough to prevent countless small injuries that could become infected and potentially fatal in a world without antibiotics or medical care. And don't overlook the social signaling aspect. Primates are visual creatures. They communicate through posture, gesture, and appearance. Body hair played a crucial role in this communication. When threatened or agitated, primates can make their hair stand on end, piloerection, making themselves look larger and more intimidating. The texture, sheen, and condition of body hair also conveyed information about health status and genetic quality. Sick or malnourished, individuals had dull, patchy fur. Healthy, well-fed individuals had glossy, full coats. This visual signaling helped potential mates assess each other and helped group members identify individuals who might be carrying diseases. So where's the evidence for all this? How do we know what our ancestors looked like millions of years ago? The fossil record provides crucial clues. While hair itself doesn't fossilize, we can infer a great deal from the bones and the environments where they're found. Early hominid fossils like Sahelanthropus chidensis, one of the oldest known members of the human family at around 7 million years old, show skeletal features consistent with both tree climbing and ground movement. The environmental context suggests they lived in mosaic habitats, areas with mixed forest and grassland. These are exactly the environments where modern apes with thick body hair thrive today. More direct evidence comes from comparative anatomy. Look at modern chimpanzees and gorillas, our closest living relatives. They're covered in dense body hair. Bonobos, equally close to us genetically, same thing. Orangutans over in Asia, thick reddish fur. The pattern is clear. Every great ape except humans has substantial body hair covering most of the body. This is what evolutionary biologists call the principle of parsimony. The simplest explanation is usually correct. If all our close relatives have thick body hair, and if the common ancestor we share with them lived 6 to 7 million years ago, then that common ancestor almost certainly had thick body hair too. For evolution to produce the naked ape you see in the mirror, something dramatic had to happen after the split. The genetic evidence seals the case. You still carry the genes for full body hair, every single one of you. In fact, you have roughly the same number of hair follicles per square inch of skin as a chimpanzee. Read that again. You have just as many hair follicles as a chimp. The difference is that most of your body hair follicles produce tiny, nearly invisible vellus hairs instead of thick terminal hairs. The genetic machinery is still there. It's just been dialed way down. Scientists have identified some of the specific genes involved. The HR gene, the hairless gene, plays a crucial role in regulating hair follicle cycling. Variations in this gene can cause the difference between thick terminal hairs and fine vellus hairs. The FGF5 gene influences hair shaft length. Mutations in this gene cause longer or shorter hair across the body. You've got working copies of all these genes. Your body still follows the basic mammalian blueprint for producing a protective hair coat. It just expresses that blueprint differently than your ancestors did. This raises a fascinating question. If our ancestors needed body hair for temperature regulation, UV protection, mechanical defense, and social signaling, and if we still carry all the genes to produce it, then something powerful must have actively selected against it. Evolution doesn't just randomly eliminate useful features. There has to be pressure, advantages to hairlessness that outweighed all the benefits of having a protective coat, and that pressure had to be strong enough to overcome millions of years of mammalian evolution, strong enough to turn a feature that had been beneficial for our ancestors into a liability, strong enough to transform us from typical apes into naked apes. Think about what this means. Somewhere between 7 million years ago, when our ancestors looked like hairy apes in the African forests, and 200,000 years ago, when anatomically modern humans appeared looking essentially like we do today, something fundamental changed. The environment shifted, or our behavior shifted, or both. And whatever changed, it made hairlessness not just acceptable but advantageous. So advantageous that individuals with less body hair survived better, reproduced more successfully, and gradually replaced their hairier relatives. This wasn't a quick process. Hair loss probably happened in stages, different body regions losing coverage at different times, driven by different selective pressures. The fossil and archaeological evidence suggests the transition was already well underway by 1.6 million years ago with Homo erectus, but might have started much earlier with Australopithecus species 3 to 4 million years ago. But here's what makes this puzzle so compelling. Evolution is conservative. It doesn't waste energy maintaining features that aren't useful, but it also doesn't eliminate features that are working perfectly well. For evolution to actively select against body hair, the costs of keeping it must have outweighed the benefits. The equation had to flip completely. The protective coat that had kept our ancestors alive for millions of years had to become a disadvantage serious enough to drive its elimination. What could possibly cause such a dramatic reversal? What environmental or behavioral changes could transform a survival asset into a survival liability? That's the central mystery we're about to explore. Because here's the thing, it wasn't just one factor, it couldn't have been. The benefits of body hair were too diverse, too important. To overcome all those advantages, multiple pressures had to align. The environment had to change. Our behavior had to change. Our diet, our social structure, our survival strategies, all of it had to shift in ways that made nakedness not just viable but superior. Over the next several segments, we're going to examine the leading hypotheses. Some of them will seem obvious, some will sound completely crazy, but each one reveals something profound about how evolution works and about the extraordinary journey that transformed our ancestors from typical apes into the strange, nearly hairless creatures watching this video right now. Because make no mistake, you are weird, bizarre even. No other primate looks like you. No other mammal your size has exposed skin across most of its body surface. You're an evolutionary oddity, a radical departure from the standard mammalian body plan. And that oddity has a story of environmental pressure, adaptive innovation, and survival against the odds. The question isn't whether we lost our body hair. We obviously did. The question is why. What happened to make nakedness a winning strategy? Let's find out. So why did we lose our fur in the first place? What evolutionary pressure was so intense that our ancestors shed the protective coat that every other primate kept? To answer that, we need to travel back about 2 to 3 million years to a time when Africa was transforming in ways that would change human evolution forever. Picture the world as your distant ancestors knew it. Dense forests stretching across much of East and Central Africa. Thick canopies overhead providing shade and protection. Trees heavy with fruits, leaves, insects, everything a primate could want within arm's reach. Your ancestors, the early hominids, were doing what their primate cousins had done for millions of years, living in and around these forests covered in protective fur, relatively safe from predators and the elements. Then the climate changed. Not suddenly, not catastrophically, but relentlessly. Over hundreds of thousands of years, Africa began drying out. The reasons were complex, a combination of shifting tectonic plates that altered atmospheric circulation patterns, changes in ocean currents affecting rainfall, and global cooling trends that locked water into ice caps rather than cycling it through tropical rain systems. The forests began to shrink, not disappearing entirely but fragmenting, breaking up into isolated patches separated by expanding grasslands. Where there had once been continuous tree cover, now there were open savannas dotted with occasional trees, vast stretches of grass and scrub under an unforgiving sun. For most forest primates, this was a disaster. Chimpanzees, gorillas, and other apes retreated deeper into the remaining forest fragments, clinging to the environments they were adapted for. But some hominids made a different choice. They moved out into the grasslands. They became savanna dwellers, and this is where the savanna hypothesis begins. The idea is elegant and on the surface makes perfect sense. Those hominids who ventured onto the grasslands faced challenges their forest ancestors never had to deal with. The most obvious one was heat. In the forest, the canopy provides shade. Temperatures stay relatively moderate even at midday. But out on the open savanna, there's nowhere to hide from the sun. When you're exposed to direct sunlight for hours, especially near the equator, heat becomes a serious problem. Now, think about what your ancestors needed to do to survive in this new environment. They couldn't just stay near water sources and wait for food to come to them. The savanna was enormous, resources were scattered. To find enough to eat, they had to cover serious distances, miles every day, walking from waterhole to feeding ground to shelter and back again. And they had to do it during the hottest parts of the day because that's when predators were less active. Here's where bipedalism becomes crucial. Your ancestors had already started walking upright before they moved onto the savanna, probably initially as a way to see over tall grass or free their hands for carrying. But out on the open grasslands, bipedalism created both an opportunity and a problem. The opportunity was efficiency. Walking on two legs uses significantly less energy than quadrupedal locomotion over long distances. Your ancestors could cover more ground with less food, crucial in an environment where resources were spread thin. But bipedalism also changed how heat affected their bodies. When you walk on four legs, most of your body is exposed to direct sunlight. When you walk upright, only your head and shoulders get the full blast of the sun. Your torso is mostly shaded by your own body. This reduces heat absorption by something like 60% during the hottest parts of the day. Clever, right? But there was still a major problem: fur. Because here's the thing about fur, it's great insulation, and insulation works both ways. In cold environments, fur keeps you warm by trapping body heat. But in hot environments, that same insulation traps heat from the sun, preventing your body from cooling down efficiently. It's like wearing a winter coat in the desert. Your ancestors were now walking long distances in intense heat, with bodies that generated significant metabolic heat from all that activity. And they were wearing fur coats. Something had to give. According to the savanna hypothesis, what gave was the fur. The theory suggests that as hominids spent more time on the savanna, natural selection began favouring individuals with less fur. Those with thinner hair coats could cool down more efficiently. They could travel farther, hunt longer, survive heat stress better. Over hundreds of thousands of years, human ancestors gradually shed most of their body hair, becoming what scientists call naked apes. But the hypothesis goes even further. It suggests that hairlessness was specifically selected for because it enabled a uniquely human hunting strategy: persistence hunting. This is where things get really interesting. Most predators on the savanna hunt in short, explosive bursts. Lions sprint after gazelles. Cheetahs accelerate to impossible speeds for brief chases. But these predators can't maintain that effort for long because they overheat rapidly. So prey animals evolved a simple defense strategy: run away, then stop and cool down. If you can survive the initial chase, you're probably safe. Humans, or rather our early ancestors, developed a different approach. Instead of short sprints, they pursued prey over vast distances, running for hours in the midday heat. Not fast enough to catch the animal immediately, but fast enough to keep it moving, preventing it from stopping to cool down. Hour after hour, the human hunters would follow, tracking footprints and visual cues, keeping the animal moving until eventually, inevitably, it collapsed from heat exhaustion. This strategy only works if the hunters can manage their own body heat, and according to the savanna hypothesis, that's exactly what hairlessness allowed. By shedding their fur and developing the most sophisticated sweating system in the animal kingdom, humans could cool themselves while running. They could dump heat through evaporative cooling faster than any other large mammal. They became the only predators capable of hunting in conditions that would kill everything else. It's an attractive theory. It explains not just why we lost our fur, but also why we evolved such extreme sweating capabilities. It ties together multiple aspects of human evolution: bipedalism, hairlessness, sweat glands, and even brain size, since efficient cooling allowed our energy-hungry brains to operate even during intense physical activity. The savanna hypothesis dominated thinking about human hairlessness for decades. It was the standard explanation you'd find in textbooks, documentaries, museums. But here's where things get complicated, because the more scientists looked at this theory, the more problems they found. Let's start with the most obvious one. There are lots of animals on the African savanna, lots of species that evolved alongside humans in exactly the same environments, facing exactly the same heat challenges, and they all kept their fur. Every single one. Zebras, wildebeest, gazelles, lions, hyenas, even wild dogs that do their own version of persistence hunting. They all have full coats of fur and they're doing fine. If hairlessness is such a huge advantage for thermoregulation on the savanna, why didn't other species evolve it? Why is it only humans? The standard response is that humans were doing something uniquely strenuous, that persistence hunting generated so much metabolic heat that only hairlessness could solve the problem. But that doesn't quite hold up under scrutiny. Wild dogs hunt in packs, running for miles in coordinated chases. They generate enormous amounts of metabolic heat. Yet they kept their fur and evolved different cooling mechanisms, primarily panting. In fact, most savanna mammals cool themselves through panting, which is actually quite efficient. It allows them to keep their insulating fur while still dumping excess heat through rapid breathing. So why didn't humans just evolve better panting instead of losing our fur entirely? Then there's the timing problem. The fossil evidence suggests hominids were already partially hairless before they fully committed to savanna living. Some researchers think hairlessness might have begun evolving while our ancestors were still spending significant time in forested environments, which doesn't fit neatly with the savanna hypothesis. There's also the issue of vulnerability. Fur isn't just for temperature regulation. It provides protection from the sun's ultraviolet radiation, from insect bites, from thorns and scrapes, from all the daily hazards of moving through rough terrain. By losing their fur, human ancestors made themselves dramatically more vulnerable to all of these threats. The savanna hypothesis needs to explain why the thermoregulation benefits outweighed all these costs, and frankly, the math doesn't always add up. Some scientists have tried to save the hypothesis by suggesting it wasn't about average conditions, but extreme ones. Maybe hairlessness wasn't necessary for everyday survival, but gave a crucial edge during the hottest days, during the most intense hunts, during those moments when 5 degrees of body temperature could mean the difference between catching prey and going hungry. Natural selection can work on rare but critical events, but other researchers remain skeptical. They point out that the archaeological evidence for systematic persistence hunting is actually pretty thin. Yes, modern hunter-gatherers in Africa sometimes hunt this way, but whether our ancestors 2 million years ago were doing it regularly enough to drive such a dramatic evolutionary change is questionable. Most of the fossil evidence suggests early hominids were more likely scavengers than endurance hunters, at least initially. Then there's the problem of partial solutions. If hairlessness evolved gradually, as it must have over hundreds of thousands of years, then early hominids went through a long period of being partially hairy. Not enough fur to provide full insulation and protection, but not hairless enough to maximize cooling through sweating. This transitional state might have actually been worse than either extreme. So what kept natural selection pushing in the hairless direction? Despite these problems, the savanna hypothesis probably contains important truths. It's hard to deny that thermoregulation was a factor in human hairlessness. Our incredible sweating capacity, unique among primates, clearly evolved for a reason. And the correlation between moving into open habitats and losing body hair is documented in other species too. Elephants, rhinos, hippos, all large savanna mammals with reduced hair cover. But increasingly, scientists think the savanna hypothesis is incomplete rather than wrong. It might explain part of why we lost our fur, but probably not all of it. Hairlessness likely evolved for multiple reasons, in response to multiple pressures, some of which had nothing to do with thermoregulation at all. Because here's the thing about evolution, it rarely has single causes. Major adaptations usually result from multiple selective pressures working together, sometimes reinforcing each other, sometimes pulling in slightly different directions until one or two pressures become dominant. The savanna hypothesis gives us one piece of the puzzle, one mechanism that probably contributed to human hairlessness. But to understand the full picture, we need to look at other hypotheses, other possible pressures that might have shaped our ancestors' evolution. Some of these ideas are even stranger than persistence hunting under the African sun. Some challenge fundamental assumptions about where and how humans evolved, and at least one involves our ancestors spending significant time in an environment where fur would have been not just inconvenient but actively dangerous, the aquatic environment. But that's a story that gets considerably weirder. Now, before we get too comfortable with the standard savanna story, we need to talk about one of the most controversial ideas in human evolution, an idea so outside mainstream thinking that it's been called everything from brilliant to completely bonkers. But here's the thing, sometimes the craziest theories teach us the most important lessons about how science actually works. So let's dive in, literally. In 1960, a marine biologist named Alistair Hardy stood up at a scientific conference and proposed something nobody was expecting. What if, he asked, our ancestors didn't just walk across the savannah? What if they waded through it? What if early humans spent significant amounts of time in water, not as occasional swimmers, but as semi-aquatic primates living on shorelines, wading through shallow waters, diving for food? The room probably went very quiet. Hardy wasn't saying humans evolved into fish. He was suggesting something more subtle, that during a critical period in our evolution, maybe 6 or 7 million years ago when we split from other apes, our ancestors lived in coastal or lakeside environments, places where water was abundant, where food could be found in shallow waters, where wading and swimming became daily activities. And this aquatic lifestyle, Hardy proposed, explained something the savanna hypothesis struggled with. Why did we lose our hair? Look at other aquatic mammals, seals, walruses, dolphins, whales, even hippos. What do they have in common? Smooth, relatively hairless skin. Hair creates drag in water. It traps air bubbles that make swimming harder. Aquatic mammals consistently evolve toward hairlessness. So maybe, Hardy suggested, humans did the same thing. He didn't publish this idea right away. He sat on it for 3 decades, knowing how controversial it would be. But in 1960, he finally went public. The scientific community's response was, let's say, lukewarm at best. Then in 1972, a Welsh writer named Elaine Morgan picked up Hardy's idea and ran with it. She wrote a book called The Descent of Woman that popularized what became known as the aquatic ape hypothesis. Morgan wasn't a scientist. She was a television writer, but she was brilliant, persuasive, and absolutely convinced that mainstream anthropology was missing something huge. She expanded Hardy's basic concept into a comprehensive theory, not just hair loss, but dozens of human features that seem bizarre for savanna-dwelling apes, but made perfect sense for semi-aquatic primates. Let's look at her evidence because, honestly, some of it is pretty compelling. First, there's our subcutaneous fat. Humans are the fattest primates by far, not just modern humans with our processed foods and sedentary lifestyles. Even lean athletic humans carry way more body fat than chimpanzees or gorillas. We have a continuous layer of fat beneath our skin, evenly distributed across our entire body. No other primate has this. No other land mammal has this, except for the ones that hibernate. But you know who does have this? Aquatic mammals. Seals, whales, dolphins. They all have thick layers of subcutaneous fat for insulation in cold water. Morgan argued this wasn't about storing energy. It was about temperature regulation in an aquatic environment. Then there's breath control. Try this experiment. Hold your breath. If you're a healthy adult, you can probably go 30 seconds, maybe a minute without too much discomfort. Trained divers can hold their breath for several minutes. Now, ask a chimpanzee to do the same thing. Well, you can't actually ask them, but researchers have tried to measure voluntary breath control in other primates. The results are striking. Chimps can't hold their breath voluntarily. They don't have conscious control over their breathing the way humans do, but aquatic mammals do. They have to. Diving requires the ability to take a deep breath, hold it while submerged, and control the release of air when you surface. Humans have this ability. Other land mammals largely don't. Morgan asked the obvious question. Why would savanna-dwelling apes need underwater breath control? Our body shape is weird too. Stand up and look at yourself in a mirror. You're streamlined, relatively speaking. Your hair, what little you have, lies flat against your body in a pattern that reduces drag when you're swimming. Your nose points downward, which keeps water out more effectively than an ape's forward-pointing nostrils. You have conscious control over your breathing, which prevents water from rushing into your lungs when you dive. Compare this to a chimpanzee. Their body hair sticks out at all angles. Their nostrils face forward. They panic in water and have to be taught to swim poorly. You, on the other hand, probably learned to swim as a child with relative ease. Human babies have a diving reflex. They automatically hold their breath when submerged. This reflex disappears as we age, but its existence suggests deep evolutionary roots. Morgan also pointed to our upright posture. Most explanations for bipedalism focus on savanna advantages, freeing hands to carry tools, seeing over tall grass, reducing sun exposure. But Morgan noted that wading is a perfect environment for evolving bipedalism. When water is chest deep, you're supported by buoyancy. Walking upright is easier than trying to move on all fours. Many primates naturally adopt upright postures when wading through water. Then there's childbirth. Human birth is notoriously difficult and dangerous compared to other primates. Our babies have huge heads that barely fit through the birth canal. Morgan suggested that water births would have made this process easier and safer, with buoyancy supporting the mother and cushioning the infant's entry into the world. Maybe, she argued, human birth evolved to be aquatic. She even tackled the mystery of speech. Humans have descended larynxes, voice boxes positioned lower in the throat than in other primates. This makes us vulnerable to choking but gives us fine control over sound production. Other animals with descended larynxes, aquatic mammals like seals and sea lions, who use them for underwater vocalizations. Maybe, Morgan speculated, human speech evolved from aquatic communication needs. The list went on. Salt appetite, unique among primates but common in marine mammals. Tears that secrete salt, possibly an adaptation for salt regulation. The ability to sweat, rare among mammals but useful for temperature regulation when you're constantly in and out of water. Even the distribution of body hair that remains, thicker on our heads, where sun protection matters most during surface swimming. Put it all together and Morgan painted a picture of human ancestors living on coastlines or beside lakes, wading through shallow waters to gather shellfish and aquatic plants, swimming to escape predators, diving for resources. Over millions of years, this lifestyle shaped our bodies, removing unnecessary hair, adding insulating fat, refining our breath control and body shape for an amphibious existence. It's a beautiful theory. Elegant, comprehensive, explaining multiple human peculiarities with a single environmental pressure. There's just one problem. Most scientists think it's completely wrong. The criticism started almost immediately and they've never really stopped. The first problem is fossil evidence, or rather the complete lack of it. If early humans spent millions of years in aquatic environments, we should find their fossils in coastal or lakeside sediments. We should see marine resources in their diet, shells and fish bones in their living sites. We should find tools designed for aquatic foraging. We don't. Early hominin fossils are found in savanna and woodland environments. Their teeth show wear patterns consistent with tough fibrous plant material, not soft aquatic foods. The stone tools we find are designed for processing land animals and plants, not harvesting shellfish. Then there's the comparative anatomy problem. When scientists look closely at human adaptations, they don't actually match aquatic mammals very well. Our subcutaneous fat is distributed differently than in seals or whales. Our breath control, while better than other primates, is nowhere near the level of truly aquatic mammals. Our body hair pattern doesn't follow the streamlining rules seen in other species that transition to water. Most damming humans are actually pretty terrible swimmers compared to animals that evolved in aquatic environments. We're slow, inefficient, vulnerable to drowning. We don't have webbed hands or feet. We don't have the physiological adaptations for diving that truly aquatic mammals possess. If we spent millions of years in water, evolution did a remarkably poor job of adapting us to that environment. The scientific community also bristled at Morgan's approach. She wasn't a trained anthropologist or evolutionary biologist. Her arguments often cherry-picked evidence that supported her theory while ignoring contradictory data. She dismissed mainstream scientists as closed-minded when they rejected her ideas, which didn't exactly endear her to the research community. By the 1990s, the aquatic ape hypothesis had been thoroughly rejected by mainstream paleoanthropology. It's not taught in university courses except as an example of how not to do evolutionary science. Most textbooks don't even mention it. The few scientists who still support versions of the theory are largely working outside mainstream institutions, so why are we talking about it? Because here's what's interesting. Even wrong theories can teach us important things. The aquatic ape hypothesis forced scientists to think harder about human hairlessness, about our subcutaneous fat, about all those weird features that don't quite fit the simple savanna story. In responding to Morgan's arguments, researchers developed more sophisticated explanations for human uniqueness. It also taught us something about how science evaluates radical ideas. Good scientific theories don't just explain observations, they make testable predictions. They lead researchers to look for new evidence that could prove them wrong. The aquatic ape hypothesis made plenty of predictions, they just turned out to be false when tested. But most importantly, it reminded us that evolution is complicated. There's rarely one simple explanation for why organisms look the way they do. Human hairlessness probably doesn't have a single cause, aquatic adaptation or otherwise. It's likely the result of multiple pressures working together over millions of years. The aquatic ape theory represents something important in the history of ideas, a reminder that being outside the mainstream doesn't make you automatically right, but it also doesn't make you automatically wrong. Sometimes the wildest ideas point toward real gaps in our understanding, even if the ideas themselves don't fill those gaps. Morgan spent decades defending her theory, writing multiple books, giving lectures, debating critics. She never convinced mainstream science, but she never stopped believing she was onto something important. She died in 2013, still convinced that humans had an aquatic past that science refused to acknowledge. Was she right? Almost certainly not, at least not in the way she imagined. But was she asking good questions? Absolutely, And sometimes that's what matters most. The real lesson here isn't about whether our ancestors waded through ancient waters. It's about how we evaluate unusual ideas, how we balance skepticism with openness, how we distinguish between creative thinking and wishful thinking. Because as we'll see, the truth about why humans lost their hair is probably weirder and more complicated than any single theory can explain. But before we get there, we need to talk about something that definitely did shape human evolution. Something crawling, biting, and absolutely everywhere. Something that made fur a liability rather than an asset. We need to talk about parasites. But there's another theory about why humans lost their hair. And honestly, when you first hear it, it sounds almost too gross to be true. But the evidence keeps piling up, and the more you look at it, the more sense it makes. This isn't about temperature regulation or swimming or running across the savanna. This is about something our ancestors dealt with every single day. Something that was killing them slowly, weakening them, making them less fit to survive in an already brutal world. Parasites, not the abstract concept of parasites, not some distant biological curiosity. I'm talking about ticks burrowing into your scalp, laying eggs, lice crawling through your body hair by the thousands, fleas that carry diseases jumping from person to person during the night, mites digging tunnels through your skin, botflies laying eggs in your hair that hatch into larvae that literally eat you from the inside out. Welcome to the parasite load hypothesis. The idea that humans lost their body hair not to stay cool, but to stay alive. Here's the thing about body hair. It's not just insulation. It's not just for display. Body hair creates an entire ecosystem. A warm, moist, protected environment, perfect for every kind of parasite that has evolved to exploit mammals. And mammals have been dealing with these parasites for hundreds of millions of years. Most species just accept it as a cost of doing business. You've got fur, you've got parasites. That's life. But early humans were in a unique situation. They were intelligent enough to notice the connection between parasites and disease. They were social enough that parasites could spread rapidly through groups. And they were already using tools and fire in ways that could help them solve the problem. They had both the motivation and the means to do something no other mammal had ever done. Get rid of the hair that was hosting their enemies. Let me paint you a picture of what parasite load looked like for our hairy ancestors around 2 million years ago. You're living in small groups, maybe 20 to 30 individuals. You sleep huddled together for warmth and protection. You share food, tools, living spaces. You groom each other, picking through each other's hair, removing dirt and parasites, except you can never get them all. For every tick you remove, there are 10 more you can't see. For every handful of lice you crush, hundreds more are laying eggs in hair follicles across your body. The parasites are winning, and they're not just annoying, they're killing you. Ticks carry diseases that cause fevers, weakness, eventually death. Lice spread typhus, which can wipe out entire communities. Fleas transmit plague. Even the minor parasites, the ones that don't carry fatal diseases, they're still draining your blood, triggering immune responses, making you weaker, less able to hunt, less capable of fighting off other infections. In a world where you're already struggling to get enough calories, where you're already dealing with predators and climate fluctuations and competition with other groups, parasites might be the thing that pushes you over the edge, the difference between your group surviving or going extinct. And here's what makes this even more interesting. You can see parasites. Unlike bacteria or viruses which our ancestors couldn't possibly understand, ectoparasites are visible. You can watch a tick swell up with blood. You can see lice moving through hair. You can feel fleas biting you. Our ancestors could make the connection. More hair equals more parasites, equals more disease, equals more death. This created a powerful selection pressure. Individuals with less body hair would have fewer places for parasites to hide. They'd be easier to inspect for parasites. Any ticks or lice trying to establish themselves would be more visible, easier to remove. Over generations, reduced body hair would mean reduced parasite load, which would mean better health, longer life, more successful reproduction. But this wasn't just natural selection operating blindly. This was sexual selection too. And this is where the hypothesis gets really fascinating. Imagine you're choosing a mate. You've got two options. Option 1 is covered in thick body hair. You can't really see their skin. You have no idea how many parasites might be living in that hair. Option 2 has much less body hair. You can see their skin clearly. You can see they don't have visible tick infestations, no obvious signs of lice. Their skin looks healthy, clean, parasite-free. Who are you choosing? Who looks like the healthier reproductive partner? Who looks like they're less likely to infect you and your children with disease-carrying parasites? The answer is obvious, and that's exactly what the evidence suggests happened. Reduced body hair became a signal of health and fitness. It became sexually attractive because it was genuinely useful information about a potential mate's parasite load. This wasn't just about appearances, this was about survival. In a world before medicine, before any real understanding of disease transmission, visible parasites were one of the few reliable indicators of health you could assess. Choosing a mate with less body hair was choosing a mate less likely to make you sick, less likely to infect your children, more likely to survive long enough to help raise those children to adulthood. And the selection pressure worked both ways. If having less body hair made you more attractive as a mate, then individuals with genes for reduced body hair would have more reproductive success. Their children would inherit those genes, would themselves have less body hair, would themselves be more attractive mates. Over thousands of generations, this feedback loop would drive the evolution of hairlessness across the entire population. Not all at once, not evenly across the body, but systematically, relentlessly, generation after generation. But here's where this gets even more interesting. We didn't lose all our hair. We kept it in specific places. Dense hair on our heads, significant hair in our armpits and groin, noticeable hair on our forearms and lower legs, though much less than our ancestors. Why? The answer tells us this wasn't just random hair loss. This was targeted evolution, solving specific problems while avoiding others. Head hair was kept because it provided crucial protection. Unlike body hair, which is relatively short and lies flat against the skin creating a warm, moist parasite haven, head hair grows long. It provides shade for the brain, protecting against both heat and UV radiation. Parasites that might live in head hair, like lice, are relatively easy to spot and remove because the hair is long and accessible. And crucially, head hair could be groomed by others. Social grooming became a bonding behavior that simultaneously reduced parasite load. The hair in our armpits and groin remained for different reasons. These areas produced specialized scent glands that became important for communication once we lost our body hair. The hair in these regions helps disperse pheromones, chemical signals that convey information about health, fertility, and genetic compatibility to potential mates. Losing this hair would have meant losing a crucial communication channel. Also, interestingly, the parasites that specialize in these areas, primarily pubic lice, can't easily transmit serious diseases. They're annoying, but not deadly. The evolutionary cost of keeping hair in these regions was lower than the cost of losing the chemical communication advantages it provided. But the body hair had to go. The dense covering that our ancestors had on their backs, chests, arms, and legs created too much habitat for too many dangerous parasites. Natural and sexual selection both push toward reducing it as much as possible while maintaining hair where it served specific protective or communicative functions. Now, here's the obvious question. If losing body hair was such an advantage, Why didn't it happen earlier? Why did humans wait until relatively recently in our evolutionary history, probably somewhere between 1 and 2 million years ago, to start losing our fur? The answer is fire and clothing. Before humans mastered these technologies, body hair loss would have been impossible. You try surviving an African night without fur, fire or clothing, you'll be hypothermic within hours, dead by morning. Body hair was an evolutionary trap. It provided essential protection against cold, against UV radiation during the day, against insects and minor injuries. The parasites it hosted were a serious problem, but losing the hair would create even more serious problems. You'd freeze, get sunburned, and be constantly bitten by insects without that protective layer. Until fire changed everything. Archaeological evidence suggests humans were using fire regularly by at least 800,000 years ago, possibly much earlier. Some sites show evidence of fire use going back 1.5 million years, though there's debate about whether these were controlled fires or just opportunistic use of natural fires. But whenever it started, fire provided artificial warmth. Suddenly, you could stay warm at night without needing a full body covering of hair. You could sleep near fires. You could carry fire with you as you moved between camps. The thermal protection that body hair provided became less critical. And then clothing emerged. We don't know exactly when, because clothing doesn't preserve well in the archaeological record. But genetic studies of clothing lice, which evolved from head lice to specialize in living in clothing, suggest humans started wearing clothes regularly, somewhere between 170,000 and 83,000 years ago. Clothing provided the final piece of the puzzle. Now you had protection from cold, from UV radiation, from insect bites, all without needing body hair. The evolutionary trap was broken. The costs of losing body hair suddenly became manageable, while the benefits of reduced parasite load remained enormous. This is why the parasite hypothesis doesn't replace the thermoregulation hypothesis, it complements it. Once humans had fire and clothing to manage temperature, reducing parasite load became the driving force. Both factors were working together, creating powerful selection for hairlessness. And the evidence keeps accumulating. Studies of modern hunter-gatherer groups who live without regular access to modern hygiene show significantly higher parasite loads in individuals with more body hair. Medical research has found that body hair increases the survival and reproduction rates of certain disease-carrying parasites. Anthropological studies show that grooming behavior, including hair removal, is universal across human cultures, suggesting deep evolutionary roots. Perhaps most tellingly, humans are unique among primates in having relatively hairless bodies. Our closest relatives, chimps and bonobos, are covered in thick body hair, despite living in similar environments and facing similar thermal challenges. The difference? They didn't develop the cultural technologies, fire and clothing, that made hairlessness survivable. And they didn't develop the social structures that made visible parasite load such an important factor in mate choice. We did. We made the evolutionary gamble that being visible, being inspectable, being obviously free of parasites was worth the costs. And we backed up that gamble with fire and clothing and social organisation sophisticated enough to make it work. So when you look at human hairlessness, you're not just seeing an adaptation for running or swimming or staying cool. You're seeing a solution to one of the oldest problems in mammalian evolution. How do you get rid of the parasites without losing the protection that hosts them? Our ancestors found an answer. They replaced biological insulation with cultural technologies. They turned visible skin into a health indicator and a sexual signal. They created a new evolutionary strategy that no other mammal had ever attempted, and it worked. Here we are, the naked apes, mostly parasite-free in our modern world, still carrying the genes that were selected for when being visibly clean meant the difference between life and death. But the revolution wasn't over. because losing our hair solved one problem but created another one just as serious. How do you stay cool when you're a hairless ape running across the African savanna under the blazing sun? But here's the thing about surviving on the African savanna during one of the most brutal climate periods in Earth's history. Being smart wasn't enough. Having better tools wasn't enough. Even developing complex social networks couldn't save you if you couldn't solve one fundamental problem: heat. Because when you're out on open grasslands, chasing animals or scavenging carcasses during the hottest part of the day, when every other predator is lying in the shade waiting for evening, your body becomes a furnace. Muscles working hard generate enormous amounts of heat, and if you can't dump that heat fast enough, you die. Not eventually, not over years. Within hours, your brain literally cooks itself. Every mammal on the planet faces this problem, but most solve it the same way. They pant. Dogs do it. Lions do it. Even our closest living relatives, chimpanzees and gorillas, rely primarily on panting to cool down. Open your mouth, breathe rapidly, evaporate water from your tongue and throat. It works well enough if you're not moving much. But try running a marathon while panting. Try chasing an antelope across open grassland for miles while breathing like a dog. You can't. Your breathing is already working overtime to supply oxygen to your muscles. You can't breathe fast enough to both oxygenate your blood and cool your body simultaneously. So our ancestors, those desperate survivors of the bottleneck, developed something revolutionary. They became the sweatiest apes on the planet. Now, all primates have some sweat, glands, but they're mostly concentrated on hairless areas, palms and soles, used primarily for grip, not cooling. Your ancestors had those too. But they also evolved something unprecedented. They covered their entire body surface with a special type of sweat gland called eccrine glands. Millions of them. Between 2 and 4 million individual microscopic cooling units distributed across almost every square inch of skin. Each gland is a tiny factory. It pulls water and salt from your blood, pumps it to the surface, and releases it as sweat. When that water evaporates, it carries heat away from your body. Pure physics. The phase change from liquid to gas requires energy, and that energy comes from your body heat. But here's where the hair becomes a problem. Because if you're covered in thick fur, like every other primate, sweat doesn't evaporate from your skin. It just soaks into the hair, drips off, wastes precious water and salt without providing much cooling. It's like wearing a wet wool sweater. You're not cooler, you're just sticky and miserable. The solution was radical. Lose the hair. Not all at once. Evolution doesn't work that way, but over hundreds of thousands of years as our ancestors spent more and more time active during the heat of the day, natural selection favoured individuals with less body hair. Less hair meant more efficient sweating. More efficient sweating meant better heat management. Better heat management meant you could keep moving when everyone else had to stop. And this created an extraordinary advantage. Because in the world of African megafauna, where antelopes and zebras and wild cattle roamed in massive herds, there was a hunting strategy that no other predator could match. Persistence hunting. Here's how it worked. You find an animal, say a kudu, or an eland, something big and meaty. You don't try to sprint after it. That's what lions do, and they fail most of the time. Instead, you just start jogging. The animal runs away, of course. It's much faster than you. But after a few hundred yards, it stops, thinking it's safe. So you keep jogging toward it. It runs again. You follow. It stops. You keep coming. Hour after hour, you maintain a steady pace. Nothing spectacular. Just a gentle jog that any reasonably fit human can sustain for hours. The animal can't understand what you're doing. It's faster, stronger, should be able to escape easily. But every time it stops to rest, there you are, still coming. And here's the critical part. The animal is panting, hard, Its cooling system forces it to choose between running and breathing. It can sprint for short bursts, but then it has to stop, stand still, pant desperately to avoid overheating. Meanwhile, you're sweating. Your cooling system works while you move. Your naked skin is radiating heat like a biological cooling tower. You can eat, drink, breathe normally, all while maintaining the same relentless pace. After 3, 4, maybe 5 hours of this, something breaks in the animal, its core temperature rises too high. The brain starts to malfunction. It becomes disoriented, staggers, collapses, and you walk up and kill it. Not with superior speed or strength, but with the most advanced cooling system in the animal kingdom. Archaeological evidence suggests our ancestors were doing this as far back as 2 million years ago. Fossil footprints in Kenya show human ancestors running across mudflats. Butchery sites show evidence of large animals killed during the hottest parts of the day, when no other predator was active. And skeletal analysis reveals that our ancestors had the long legs, short toes, and spring-like foot arches perfect for sustained distance running. We became endurance specialists, the marathon runners of the predator world, and our naked, sweaty skin was the technology that made it possible. But this evolutionary strategy came with serious trade-offs, because mammalian fur isn't just insulation. It's protection. Protection from cold, from sunburn, from biting insects, from thorns and scrapes. Losing it meant becoming vulnerable in new ways. The cold was probably the first problem. Naked skin loses heat rapidly when temperatures drop. This would have been fine in equatorial Africa during the day, but nights on the savanna can be cold. Early mornings can be frigid. Our ancestors needed solutions. This is probably when they started using fire more systematically, not just for cooking or keeping predators away, but as portable warmth. Archaeological sites from around 800,000 years ago show evidence of controlled fire use becoming common, not occasional, but regular. Every major habitation site has hearths. They also probably started using animal skins as insulation long before they developed true clothing. Drape a hide over your shoulders at night, huddle close to the fire, and suddenly nakedness and cool weather becomes manageable. But sunburn was perhaps the even bigger challenge, because the African sun is brutal. UV radiation that can blister unprotected skin in hours cause skin cancer over years. Fur-covered mammals don't worry about this. Their coats block most UV radiation. The solution was melanin, lots of it. Natural selection favoured darker skin pigmentation in populations living near the equator. Melanin acts like biological sunscreen, absorbing UV radiation before it can damage DNA in skin cells. Within probably just a few thousand generations, our ancestors went from having light skin under dark fur like modern chimpanzees to having the darkest skin of any primate species. This is why all ancient African populations had very dark skin, not because of any cultural or social factors, but because in equatorial Africa, light-skinned individuals would have developed skin cancers and died before reproducing. Dark skin wasn't an adaptation to being naked, it was a necessary consequence of it. But there was one place where hair remained critically important: the head. Because your brain is the most heat-sensitive organ in your body, it's also the most metabolically active, generating tremendous amounts of heat even at rest. Put it in direct sunlight on the African savanna, and you've got a serious problem. Your brain needs cooling, but it also needs protection from direct solar radiation. The solution was elegant. Keep a thick mat of hair on top of the skull, creating an insulating air layer between the sun and the scalp. The hair shades the head, reduces direct heat absorption, while allowing air circulation underneath. Meanwhile, sweat glands in the scalp and face provide evaporative cooling. This is why humans universally have hair on their heads, even populations that have lived in hot climates for hundreds of thousands of years. It's not decorative, it's not vestigial, it's critical temperature regulation equipment for your most important organ. And it's why male pattern baldness is so frustrating from an evolutionary perspective. You're losing your brain's sun hat. In ancestral environments, this would have been a serious problem, but by the time most men lose their hair, they've already reproduced, so natural selection doesn't care. The real proof that this cooling system upgrade was revolutionary comes from comparing human athletic performance to other animals. In sprint speed, we're pathetic. Dozens of animals can outrun us in short distances, but in endurance, we're unmatched. A healthy human can run a marathon in under 3 hours. Elite athletes can do it in just over 2. And ultra-marathon runners regularly complete 100-mile races in mountainous terrain. No other primate can do anything close to this. Chimpanzees are much stronger than humans, but they can barely jog for more than a few minutes before overheating. Even animals specifically adapted for endurance like wolves or wild dogs can't match human performance in hot weather. Put a human and a horse in a marathon on a hot day, and the human wins. We've literally beaten horses in sanctioned races, not because we're faster, but because we can maintain our cooling system while running. This advantage was so significant that it may have driven other aspects of human evolution. Some researchers argue that our large brains, which generate enormous amounts of heat, only became possible once we developed efficient whole-body cooling. You can't run a bigger processor without better cooling, whether you're talking about computers or brains. The metabolic cost of sweating is also significant. Each litre of sweat represents about 580 calories of heat energy removed from your body. But producing that sweat requires water and salt, both precious resources in many environments. An active human can sweat up to 3 litres per hour in extreme heat, losing not just water, but critical electrolytes. This created new dietary pressures. Our ancestors needed reliable access to water, obviously. But they also needed salt, lots of it, much more than other primates. This might explain why humans are one of the few mammals that actively seeks out salt, why we find salty foods so appealing. We're not just indulging a preference, we're responding to a biological necessity created by our eccrine sweat glands. Some researchers think the need for salt may have driven early humans toward coastal environments, where salt water and salt-rich seafood were abundant. Others argue it encouraged systematic hunting of large mammals, whose blood and organs provided concentrated sources of sodium. Either way, becoming the naked, sweaty ape created a cascade of secondary adaptations. We needed fire for warmth. We needed dark skin for sun protection. We needed hair on our heads for brain cooling. We needed reliable access to water and salt. Each solution created new challenges, new selection pressures, new evolutionary directions. But the payoff was extraordinary. We became the most efficient long-distance athletes in the animal kingdom. We could hunt during the heat of the day when other predators rested. We could travel vast distances, migrating into new territories, following resources across landscapes that would have been impossible for other primates to traverse. Our sweat glands, more than almost any other adaptation, made us human. They allowed us to leave the forests. They enabled our brains to grow larger. They gave us access to protein sources that would have been impossible to obtain otherwise. We became naked not despite the challenges of survival, but because nakedness, combined with our revolutionary cooling system, was the ultimate survival technology. In a world where heat management meant the difference between eating and starving, between reproducing and dying childless, sweat was more valuable than fur. And every time you work up a sweat, every time you feel that cooling moisture on your skin, you're experiencing the same technology, that kept your ancestors alive through the worst climate disaster in human history. You're feeling evolution in real time, the same cooling system that let someone 900,000 years ago run down their dinner in the midday heat. You're still a naked ape, still sweating for survival, still carrying the adaptations that made us human. But nakedness alone wouldn't have been enough, because there was another force at work, another pressure pushing our ancestors toward bare skin. And this one had nothing to do with hunting or heat management or survival. This one was about something far more unpredictable, far more powerful: attraction. But here's where the story of human nakedness gets really interesting. Because all those survival explanations, the cooling systems, the parasite resistance, the adaptation to new environments, they only tell part of the story. There's another force at work in human evolution, one that's often overlooked but potentially just as powerful as natural selection itself. Sexual selection. And it might be the real reason we find ourselves attracted to smooth, hairless skin. Darwin figured this out back in the 1870s. He noticed that many traits in nature couldn't be explained by survival advantages alone. The peacock's tail doesn't help it survive. Actually, it does the opposite. That massive, colourful display makes the bird slower, more visible to predators, more vulnerable. But peacocks have those tails anyway because peahens find them irresistible. The trait survives not because it helps individual peacocks live longer, but because it helps them reproduce more successfully. Darwin proposed that human nakedness might work the same way. Not primarily a survival adaptation, but a sexual one. Something that evolved because our ancestors found it attractive, even if it didn't necessarily help them survive better. And the more you look at human hair loss patterns, the more this explanation starts making sense. Think about it. If hair loss was purely about cooling or parasite resistance, you'd expect it to be distributed evenly across the body, or concentrated in the areas that need cooling most, like the torso and limbs. But that's not what happened. Instead, we lost hair in very specific patterns that differ dramatically between males and females. Men retain more facial hair, chest hair, and body hair generally. Women retain less, developing smoother skin across most of their bodies. But both sexes keep the hair on their heads, and we retain it in specific patches that seem to serve more as signals than as functional equipment. This is the signature of sexual selection. Different patterns in males and females, retention of features that serve as displays or signals, loss of features that might obscure the very signals that potential mates are looking for. Our ancestors weren't just losing hair randomly, they were sculpting their appearance based on what they found attractive in potential partners. And here's the really clever part. Bare skin isn't just about appearance, it's about information. Hair hides things. It conceals the condition of the skin underneath, masks changes in colour, obscures the fine details that might tell you something important about the person you're looking at. When our ancestors lost their fur, they became readable in ways that had never been possible before. Suddenly health became visible. Skin conditions, parasites, infections, all the things that might indicate a poor genetic match or compromised immune system, they were right there on display. You couldn't hide them under a layer of fur anymore. A potential mate with clear, unmarked skin was advertising something valuable. A robust immune system, good health, genetic fitness. Age became visible too. Skin changes as we get older. It loses elasticity, develops wrinkles, changes texture and tone. In a furred animal, these changes happen mostly out of sight. But in naked humans, aging is obvious. This might sound like a disadvantage, but from an evolutionary perspective, it's incredibly useful information. If you're choosing a mate, you want to know how old they are. Fertility declines with age, especially in females. Being able to assess a potential partner's age at a glance helps you make better reproductive decisions. And then there's the most remarkable aspect of bare skin. It blushes. This might be the most uniquely human feature of all. When we're embarrassed, aroused, angry, or experiencing strong emotions, blood rushes to the skin of our faces, necks, and sometimes our chests. We turn red, visibly, obviously red. No other species does this quite like we do, and it only works because our skin is bare. Darwin was fascinated by blushing. He called it the most peculiar and most human of all expressions, and he was right to be intrigued. Blushing is essentially involuntary emotional honesty. You can't fake it, and you can't completely suppress it. When your face turns red, everyone around you knows you're experiencing something intense. It's a signal that can't be controlled, which makes it incredibly reliable. In the context of sexual selection, blushing becomes a powerful tool for assessing sincerity and emotional investment. A potential partner who blushes when they look at you is revealing genuine interest. Someone who remains pale and unmoved might be less invested. Over hundreds of thousands of years, our ancestors who could read these signals and respond appropriately would have made better mating decisions, had more successful relationships, raised more offspring. But sexual selection didn't just favour the ability to read signals, it favoured the signals themselves. Individuals with clearer skin, more responsive blushing, more visible emotional displays would have been seen as more honest, more trustworthy, more desirable. This created a feedback loop. Bare skin became attractive because it revealed information. Once it became attractive, having even clearer, more expressive skin became more advantageous. The trait reinforced itself, generation after generation. And the evidence is everywhere. Nearly every human culture that's ever been studied shows preferences for smooth, clear skin. Yes, beauty standards vary. Different cultures emphasize different features, prefer different body types, have different ideas about ornamentation and modification. But the preference for healthy-looking, unblemished skin appears to be universal. It shows up in art, in mate selection studies, in the cosmetics and grooming practices that emerge independently in cultures around the world. This universality suggests something deep and ancient. Not a learned preference, but an evolved one. Our brains are wired to find clear skin attractive, because for hundreds of thousands of years, clear skin has been a reliable indicator of health, youth, and genetic quality. The preference became hardwired through natural selection. But here's where it gets even more interesting. The sexual selection explanation doesn't contradict the survival explanations we've already explored. It complements them. Evolution is messy. Multiple pressures operate simultaneously, pushing and pulling traits in different directions. The final result is usually a compromise and optimization across multiple selective forces. So maybe hairlessness started as a cooling adaptation. Better thermoregulation gave our savanna-dwelling ancestors a survival advantage. But once some hair was lost, sexual selection could amplify the trend. Individuals with even less hair were easier to read, more attractive as mates, more successful at reproduction. The two forces worked together, survival and sexual selection reinforcing each other, driving hair loss further and faster than either force could have done alone. This is what biologists call a mosaic of selective pressures. Not one single explanation, but multiple forces operating simultaneously, each contributing to the final outcome. And sexual selection adds something the purely survival-based explanations can't fully account for. It explains the variability between individuals, the gender differences in hair retention patterns, and most importantly, it explains why we find nakedness beautiful. Because here's the thing about sexual selection. It can drive traits to extremes that pure survival selection never would. A peacock's tail is absurdly large, impractically colourful, a clear survival disadvantage. but it exists anyway because the sexual selection pressure is strong enough to overcome the survival costs. The reproductive advantage outweighs the survival disadvantage. The same logic might apply to human nakedness. Being completely hairless probably wasn't optimal for survival. There are situations where body hair would have been useful: warmth during cold nights, protection from sun exposure, cushioning against minor injuries. But if being hairless made you significantly more attractive to potential mates, the reproductive advantage would outweigh those survival costs. You might die slightly younger, but you'd have more children. From evolution's perspective, that's a winning trade, and once the preference was established, it became self-reinforcing. Each generation, individuals with less body hair were more attractive, had more mating opportunities, left more descendants. Those descendants inherited both the genes for reduced hair growth and the preferences that made hairlessness attractive. The trait and the preference for the trait evolved together, locked in a feedback loop that drove both to extremes. This also explains something puzzling about human sexuality. We're one of the few species that mates face-to-face as a common practice. Most mammals mate from behind, limiting visual contact, but humans adopted frontal mating as a primary position, maximizing eye contact and the ability to read facial expressions during intimate moments. Why? Maybe because we'd become so dependent on visual communication through bare skin that we needed to maintain that connection even during reproduction. The ability to see your partner's face, to read their emotional responses through blushing, skin flushing, and facial expressions, created stronger pair bonds, better coordination, more successful relationships. Couples who could communicate effectively in this way raised more children together. The behavior spread. And there's one more piece of evidence that sexual selection played a major role. The hair we kept isn't random. We retained head hair, which can grow extremely long. We retained pubic and axillary hair, which appears during sexual maturity. These retention patterns suggest signaling functions: head hair as a display of health and grooming ability, secondary sexual hair as a marker of reproductive maturity and capability. In other words, we didn't just lose hair everywhere. We kept it precisely where it could serve as a sexual signal while losing it everywhere else, to maximize the readability of our skin. That's not the pattern you'd expect from a purely survival-driven adaptation. That's the pattern of sexual selection carefully sculpting appearance to maximize reproductive success. So perhaps the real answer to why humans lost their fur isn't found in any single explanation. Not just cooling, not just parasites, not just aquatic adaptations or sexual preferences. All of these forces work together, each reinforcing the others, creating a cascade of changes that transformed our ancestors from furred apes into naked humans. But sexual selection adds the final piece. It explains not just why we lost our hair, but why we find bare skin beautiful, why we're attracted to smooth, clear skin, why the sight of healthy naked skin triggers something deep and primal in our brains. We're naked because being naked made us more attractive, and being more attractive helped our ancestors leave more descendants, who were also naked, and also found nakedness attractive. For hundreds of thousands of years, this feedback loop has been running, refining our preferences, reducing our body hair, making us more and more committed to this strange naked existence. But nakedness created new problems. Without fur, our ancestors were vulnerable to cold, to sun exposure, to all the environmental hazards that body hair had protected against. How did they survive? The answer lies in one of humanity's most important innovations, an invention that would change everything about how we lived and who we were: fire. But here's where the story of human nakedness gets really interesting, because losing your hair is one thing. Surviving without it in freezing environments is something else entirely. Think about it. Your hairless ancestors were spreading out of Africa into regions where winter temperatures could drop below freezing. where Ice Age winds could strip heat from exposed skin in minutes, where the very adaptations that helped them survive the African savanna, the sweating, the bare skin, the efficient cooling system, should have killed them the moment they encountered their first European winter. So how did they survive? The answer comes in two parts, and both of them represent the moment when human evolution stopped being purely biological and started becoming cultural, when we began adapting not by changing our bodies, but by changing our behaviour. The first part is fire. Now, humans didn't invent fire. Lightning had been setting forests ablaze for hundreds of millions of years. Animals had been fleeing from wildfires since the first plants colonised land. But somewhere around 400,000 years ago, maybe earlier, your ancestors figured out something revolutionary. They learned to control it. The archaeological evidence is scattered but compelling. Hearth sites in caves across Africa, Europe and Asia, showing repeated intentional use of fire. Not just opportunistic exploitation of natural fires, but systematic fire management. Our ancestors were capturing fire, feeding it, keeping it alive through the night, transporting it to new locations. This was technology on a scale that had never existed before, and it changed everything. Because here's what fire does. It extends your range. Suddenly you can survive in environments that would otherwise kill you. That cave that's too cold to inhabit, light a fire and it becomes a home. That meat that would rot in a day, cook it and it lasts longer, becomes easier to digest, provides more calories per bite. Those long winter nights that would freeze you solid, gather around the flames and survive until morning. Fire made nakedness possible in cold climates. Your hairless ancestors could spread into Europe, into Asia, into regions where their cousins, the Neanderthals, needed massive body mass and enormous caloric intake just to maintain body temperature. And they could do it while remaining relatively gracile, relatively light, relatively efficient. But fire alone wasn't enough, because you can't carry fire everywhere. You can't swim with it, can't hunt with it, can't sleep wrapped in it. For that you needed something else. You needed clothing. Now clothing doesn't fossilize. Organic materials, leather, plant fibers, animal skins, they rot away almost immediately in archaeological terms. So for the longest time, researchers had no idea when humans started wearing clothes. Was it 50,000 years ago? 100,000? Longer? Then geneticists figured out something brilliant. They studied lice. See, humans have two distinct types of lice: head lice, which live in scalp hair, and body lice, which live in clothing. These two species are closely related, but they've diverged into separate populations adapted to different environments, and by analysing their DNA, researchers could calculate when they split apart. The answer: somewhere between 170,000 and 83,000 years ago. That's when human body lice evolved, which means that's when humans started wearing clothing regularly enough that lice could adapt to this new ecological niche. Think about what this means. Your ancestors were walking around mostly naked in Africa for hundreds of thousands of years, maybe millions. Then, as they spread into new environments, as they encountered colder climates and harsher conditions, they started wrapping themselves in animal skins, plant fibers, whatever they could find to retain heat. And once they had clothing, something remarkable happened. The evolutionary pressure to maintain body hair essentially disappeared. See, body hair is expensive. Each hair follicle requires resources to grow and maintain. Each hair carries risk, trapping parasites and pathogens. In a world where you have fur coats made from actual fur, the biological fur coat your ancestors had been carrying around for millions of years became redundant. This created a feedback loop. Nakedness encouraged clothing innovation, because hairless humans got cold and needed artificial insulation. But clothing reduced the evolutionary advantage of body hair, making populations even more hairless over time. Cultural evolution and biological evolution lock together in a spiral of mutual reinforcement. The archaeological record shows this technological explosion happening in real time. By 30,000 years ago, humans were creating sophisticated clothing with bone needles, carefully tailored to fit their bodies. Cave paintings show people wearing elaborate garments, boots, possibly hats. These weren't just wrapping themselves in random animal skins anymore. They were designing, manufacturing, innovating, and the more sophisticated their clothing became, the less they needed body hair. Natural selection stopped favouring individuals with thick body hair and started favouring, or at least not selecting against, individuals with less. Within populations spreading into cold climates, you'd expect heavy selection for maintaining body hair. Instead, you see the opposite. Humans in Ice Age Europe were just as hairless as their cousins in tropical Africa. Technology had replaced biology as the primary mode of adaptation. But here's where it gets complicated, because not all human populations lost body hair at the same rate or to the same degree. Even today you see significant variation. Some populations, particularly those from East Asia, tend to have less body hair. Others, particularly those from the Middle East and Mediterranean, tend to have more. Why? Part of the answer has to do with how recently different populations adopted sophisticated clothing technologies. Groups that had been wearing clothes for longer periods had more generations for natural selection to reduce body hair. Groups that adopted clothing more recently retained more of their ancestral hairiness. But there's another factor at play, one that has nothing to do with temperature regulation and everything to do with something humans couldn't survive without. Vitamin D. Your body manufactures vitamin D when ultraviolet light from the sun hits your skin. It's a crucial process. Without adequate vitamin D, you develop rickets, bone deformities, immune system problems. Your ancestors in tropical Africa got plenty of UV exposure, so much that they developed dark skin pigmentation to protect against sun damage. But when humans moved into northern latitudes, into regions where winter sun barely rises above the horizon, where cloud cover blocks UV radiation for months at a time, they faced a crisis. Their dark skin, perfectly adapted for African sun, blocked too much of the limited UV light available. They weren't producing enough vitamin D. Natural selection responded quickly. Within a few thousand generations, populations in northern Europe developed pale skin that allowed more UV penetration. But skin wasn't the only thing that changed. Body hair, which also blocks UV light from reaching skin, became disadvantageous in these low sunlight environments. This created different selection pressures in different regions. In equatorial populations, there was no vitamin D crisis, so less pressure to reduce body hair. In far northern populations, vitamin D was critical, so stronger selection for reduced hair coverage. Meanwhile, populations in middle latitudes, places with moderate sunlight and seasonal variation, experienced intermediate pressures. Some body hair was acceptable, particularly in areas that were usually covered by clothing anyway. The result is the patchwork of human hairiness we see today. Not random variation, but the product of different populations solving the same basic problems: temperature regulation, parasite control, vitamin D synthesis, using slightly different combinations of biological and cultural adaptations. But here's what makes this story remarkable. For the first time in human evolution, cultural innovation was driving biological change as much as biology was constraining culture. Your ancestors weren't just passively adapting to their environment anymore. They were actively reshaping it, creating artificial environments, clothing, shelters, fire-managed spaces, where biological adaptations became less important than technological ones. This was a revolution. For billions of years, life on Earth had evolved through natural selection, acting on random genetic variation. Species that couldn't adapt to their environment died out. Species that could survive and reproduce passed on their genes. But humans had discovered a shortcut. Instead of waiting thousands of generations for beneficial mutations, they could just invent solutions. Cold climate. Invent clothing. Dark winters. Invent fire. Nutritional deficiencies. Invent cooking techniques that made nutrients more bioavailable. Culture was replacing biology as the primary adaptive mechanism, and once that process started, it accelerated exponentially. Within a few thousand years of developing sophisticated clothing, humans were building permanent shelters. Within a few thousand more, they were domesticating plants and animals. Within a few thousand after that, they were creating cities, writing systems, complex technologies. Each innovation reduced the importance of biological adaptation and increased the importance of cultural learning. And nakedness, that strange loss of body hair that made humans so vulnerable compared to their hairy ancestors, became not a liability but an advantage, a sign that we had transcended the normal rules of evolution and begun writing our own. But the loss of body hair wasn't the only change our ancestors were going through. It wasn't happening in isolation. Multiple evolutionary pressures were operating simultaneously, pushing human bodies in strange and unprecedented directions. What emerged wasn't the result of any single factor, but the product of a complex interaction between climate, parasites, sexual selection, and cultural innovation. And that brings us to the final piece of the puzzle. Here's the thing about evolutionary biology. We love a good story. We love finding that one perfect explanation that ties everything together with a neat bow. The savanna hypothesis, the aquatic ape, the parasite problem. Each one sounds so compelling on its own, so elegantly simple. But evolution doesn't work like that. Evolution doesn't read narratives. It doesn't care about our need for tidy explanations. Reality is messier, and honestly, way more interesting. Because the truth about why humans lost their fur isn't hiding in one single theory. It's scattered across all of them. Each hypothesis we've explored contains a piece of the puzzle. The question isn't which one is right. The question is how they all work together, reinforcing each other, creating feedback loops that ultimately transformed us into the naked apes we are today. This is what scientists call the mosaic theory of human hairlessness. Not one pressure, but multiple pressures. Not one solution, but a cascade of interconnected adaptations. Not a sudden change, but a gradual transformation spanning millions of years, with different selective pressures dominating at different times and in different populations. Let's break this down. Start with thermoregulation, the cooling problem. Around 2 million years ago, your ancestors are moving out of the forests, spending more time in open grasslands, hunting and scavenging under the brutal African sun. They're also getting bigger brains which generate enormous amounts of heat. A brain that size working overtime in midday heat? That's a recipe for disaster. Natural selection starts favouring individuals with less body hair and more sweat glands. Not all at once, but generation by generation. The hairiest individuals struggle more with overheating. They hunt less effectively. They think less clearly. They have fewer surviving children. Meanwhile, the individuals with slightly less hair, slightly better sweating capacity, they've got an edge. A small edge. Maybe, but over thousands of generations, small edges compound into major transformations. But here's where it gets interesting. Once you start losing hair for cooling purposes, you accidentally solve another problem. Parasites. Those ancestors living 2 million years ago, they were probably crawling with lice, fleas, ticks, all the delightful passengers that come with fur. Fur is basically a paradise for ectoparasites. Warm, protected, lots of places to hide and breed. When hair starts thinning out for thermoregulation reasons, Suddenly those parasites have fewer places to live. The individuals with less hair aren't just cooler, they're also carrying lighter parasite loads. They're healthier. Their children survive better. Their immune systems aren't constantly fighting infections from flea bites and tick-borne diseases. So now you've got two separate pressures both pushing in the same direction. Cooling and parasite reduction, working together, reinforcing each other. This is what evolutionary biologists call synergy. When multiple selective pressures align, evolution accelerates. Changes that might have taken tens of millions of years can happen in just a few million. But wait, there's more. Because as body hair is disappearing, something else is becoming visible. Skin. Naked skin that can change colour with emotion, health, and arousal. Blood flowing close to the surface, creating visual signals that would have been invisible under fur. This opens up entirely new possibilities for communication and sexual selection. Think about blushing. That's not a cooling mechanism. That's a social signal, an involuntary advertisement of embarrassment or attraction. Or consider how visible skin conditions become when there's no fur to hide them. Suddenly potential mates can assess each other's health more accurately. That rash, that scar, those parasites you're still carrying, can't hide them anymore. This creates what evolutionary biologists call honest signaling. Naked skin is harder to fake than fur. It reveals your true condition for better or worse. Sexual selection kicks in. Maybe the first individuals to lose significant body hair were selected against initially. Maybe they looked weird, unattractive by the standards of their hairy peers. But once hairlessness started correlating with other desirable traits, better cooling capacity, lower parasite loads, visible health signals, the aesthetic preferences shifted. What was once strange became attractive. What was once abnormal became the new standard. And here's where fire and clothing enter the story. Because here's a paradox. Losing hair makes you vulnerable to cold, especially at night, especially during the frequent climate fluctuations your ancestors endured. Without some way to compensate for that heat loss, extensive hair loss would be actively harmful in many environments, but around 1.5 million years ago, your ancestors are mastering fire. By 500,000 years ago, they're using it systematically. By 100,000 years ago, they might be making simple clothing from animal skins. Fire and clothing solve the cold problem. They make hairlessness possible in ways it wouldn't have been before. This creates another feedback loop. Once you can stay warm artificially, the evolutionary pressure to maintain thick body hair decreases. Individuals born with genes for reduced hair aren't penalized anymore. In fact, they might have advantages. Less hair means you can switch more rapidly between cooling and warming strategies. You can hunt in the heat of midday, then huddle by a fire at night. You're more adaptable, more flexible in your responses to environmental challenges. This is the mosaic in action. Thermoregulation driving initial hair loss. Parasite reduction reinforcing that change. Sexual selection making it attractive. Cultural innovations like fire and clothing, removing barriers that would have prevented further hair loss. Each pressure operating on different timescales, in different populations, but all pushing generally in the same direction. But, and this is crucial, it didn't happen uniformly. It didn't happen all at once. The genetic and archaeological evidence tells us that hair loss was gradual, patchy, and varied significantly between different human populations. The first hair to go was probably body hair, especially on the torso and limbs. That's where you need the most cooling, and where parasites cause the most problems. This might have started 2 million years ago with early Homo erectus populations. Archaeological evidence suggests these early humans had already developed extensive sweating capacity, which doesn't work nearly as well with thick fur. Head hair, though, that stuck around. In fact, head hair might have actually become thicker and longer in some populations. Why? Because your brain is your most heat-sensitive organ, and direct sun exposure on a naked scalp is a great way to cook it. Head hair provides shade and insulation, protecting against both overheating and sunburn. Natural selection kept it firmly in place. Underarm and pubic hair also retained, probably for different reasons. These areas have specialized apocrine sweat glands that produce scent signals. The hair helps disperse those scents, playing a role in sexual signaling and individual recognition. It's not about temperature regulation at all. It's about communication, about advertising your presence and your reproductive status to potential mates. Eyebrows and eyelashes, obviously protective. They keep sweat, rain, and debris out of your eyes. Any mutation that reduced them would be actively harmful, so natural selection maintained them despite the general trend toward hairlessness elsewhere. This selective retention tells us something important. Evolution isn't random. It's not just deleting hair everywhere, because hairlessness is generally beneficial. It's making fine-tuned adjustments, preserving hair where it serves important functions, eliminating it where the costs outweigh the benefits, and the timeline spread across millions of years. Early Homo erectus around 2 million years ago probably had significantly reduced body hair compared to their ancestors. But they weren't as naked as modern humans. Homo heidelbergensis, around 600,000 years ago, likely showed even less hair. By the time Homo sapiens emerged around 300,000 years ago, the basic pattern of human hairlessness was probably established, but there was still significant variation between populations. That variation persists today. Not all humans are equally hairless. Northern European populations tend to have lighter, finer body hair. Mediterranean populations often have darker, coarser hair that's more visible. East Asian populations frequently show reduced body hair compared to other groups. African populations show enormous variation, from relatively hair-free to quite hirsute, depending on specific ethnic groups. This variation isn't random. It reflects different evolutionary histories, different local selective pressures, different periods of isolation and admixture. The genetic basis of human hairlessness involves at least dozens of genes, maybe hundreds, each contributing small effects. Some genes control hair follicle density, others affect hair shaft thickness. Still others determine when hair follicles shut down during development. Different populations have different combinations of these variants, creating the spectrum of hairiness we see in modern humans. But here's what's really fascinating. We're still evolving. Human hair patterns are still under selection, still changing in response to environmental and cultural pressures. In industrialized societies where indoor climate control is universal, where we spend most of our lives in temperature-regulated buildings, the selective pressure for or against body hair is probably minimal. Random genetic drift might be increasing variation rather than reducing it. In other populations, though, selection might still be operating. Groups living in extreme environments, very hot deserts, very cold climates, might still be evolving adaptations related to hair density and distribution. The Inuit people of the Arctic, for instance, show genetic adaptations to extreme cold that might include modifications to hair follicle activity and distribution. And sexual selection? That's definitely still operating. Cultural preferences for body hair vary enormously. In some cultures, body hair on men is considered attractive, a sign of masculinity and virility. In others, hairlessness is preferred. For women, most modern cultures favor reduced body hair, but historical preferences varied widely. These cultural pressures can translate into real evolutionary change over time if they consistently affect reproductive success. The genetic complexity of human hairlessness also tells us something profound about how evolution works. This wasn't a simple mutation. There's no single hairlessness gene that switched on 2 million years ago. Instead, hairlessness emerged from the accumulation of hundreds or thousands of small genetic changes, each slightly modifying some aspect of hair growth distribution, or retention. Some mutations reduced follicle density, others shortened the growth phase of hair follicles. Still others changed the balance between thick terminal hairs and thin vellus hairs. This gradual multigenic basis meant the change could be fine-tuned by natural selection. Populations could evolve more or less hairlessness depending on local conditions. Different hair patterns could emerge in different regions of the body. The system could respond flexibly to changing selective pressures rather than being locked into one pattern. It also meant that hairlessness could evolve alongside other adaptations without causing catastrophic problems. If body hair had disappeared overnight due to a single dramatic mutation, the individuals carrying that mutation would have died from exposure. But gradual reduction over millions of years, coordinated with the development of sweating, cultural adaptations like fire and clothing, and behavioral changes like seeking shade, that was survivable. That was actually beneficial. So what does the naked ape teach us about human evolution? First, that complexity is the rule, not the exception. Simple explanations are satisfying, but reality usually involves multiple interacting factors. Second, that cultural and biological evolution are deeply intertwined. Fire and clothing weren't just tools we invented, they were evolutionary forces that shaped our bodies. Third, that evolution is ongoing. We're not the finished product. We're still adapting, still changing, still responding to selective pressures, both natural and cultural. Most importantly, our hairlessness teaches us about the power of feedback loops in evolution. One adaptation enables another, which reinforces the first, which opens up possibilities for a third. Better cooling allows longer hunts, which provides more food, which supports bigger brains, which enables cultural innovations like fire, which makes further hair loss possible, which improves parasite resistance, which improves overall health, which increases reproductive success. Round and round, each change amplifying the others, accelerating the transformation from hairy ape to naked ape. This is evolution not as a ladder, with one adaptation stacked neatly on another, but as a web, with multiple threads connecting, reinforcing, occasionally contradicting each other. It's messy, it's complicated, it doesn't make for simple stories, but it's real, and it's how we became human. So here we are, after millions of years of evolution, after countless generations of trial and error, after environmental pressures and selective forces we can barely imagine, we're left standing here, naked, mostly hairless, definitely weird compared to almost every other mammal on the planet. And the truth? We still don't have one perfect answer. Because here's what we've learned. The savanna hypothesis explains some things brilliantly. The need for better cooling as we started running across open grasslands, hunting prey through the hottest parts of the day when other predators were resting. That makes sense. The reduction in body hair combined with our uniquely powerful sweating system gave us an endurance advantage that no other predator could match. But the aquatic ape theory also explains things the savanna hypothesis doesn't. Why our remaining hair follows water flow patterns. Why we have subcutaneous fat like marine mammals. Why human babies can hold their breath instinctively. Maybe our ancestors did spend significant time in and around water, exploiting coastal and lakeside resources that other species ignored. Then there's the parasite hypothesis. Less hair meant fewer places for ticks, lice, and disease-carrying insects to hide. In dense populations where diseases could spread rapidly, hairlessness might have been the difference between life and death. Natural selection doesn't care about looking good. It cares about not dying before you reproduce. And sexual selection? The social signaling advantages of visible skin? The way hairlessness made humans better at reading emotions, detecting health status, choosing optimal mates? That probably played a role too. Evolution rarely has just one pressure at work. It's usually a whole mess of different factors all pushing in roughly the same direction. The real answer is probably what scientists call the mosaic theory. Multiple pressures, acting over millions of years, all favouring hairlessness for different reasons in different contexts. Better cooling in open environments, reduced parasite loads in social groups, enhanced communication through visible facial expressions, sexual selection for novelty and youthfulness, feedback loops with clothing technology and fire use, all of it together, generation by generation, selecting for the naked apes we became. But here's what's really beautiful about this mystery. It reveals something profound about human evolution and human nature. We're not the product of one simple environmental pressure. We're not like the giraffe that evolved long necks for one obvious reason. We're complicated. We're the result of millions of interlocking factors, environmental and social and technological, all influencing each other in ways we're still trying to understand. Our hairlessness isn't just a biological curiosity. It's a window into what makes us human. The fact that we could survive losing our fur shows how adaptable we became. We invented clothing and mastered fire to protect our vulnerable naked skin from cold and sun. We developed complex social systems that depended on reading subtle skin color changes during emotions. We created cultures that decorated and adorned the bare skin that made us unique. We turned a potential weakness into a strength. That's the human pattern. Right there. That's what we do. We take challenges and transform them into opportunities through intelligence, cooperation, and innovation. Every time you look at your naked arm, your relatively hairless legs, your mostly bare chest or back, you're looking at evidence of this incredible evolutionary journey. You're seeing the physical manifestation of millions of years of natural selection, millions of decisions made by ancestors you'll never know, millions of tiny changes that accumulated into something unprecedented in the mammal world. We became naked apes because the world pushed us in that direction. But we survived being naked apes because we were clever enough, cooperative enough, and creative enough to adapt. And that's the naked truth. Now, if you've made it this far into our journey through human evolution, if you've stayed with us through savannas and shorelines, parasites and persistence hunting, chromosomal fusions and climate disasters, then you're exactly the kind of curious person we're making these videos for. Hit that like button if you enjoyed exploring this mystery with us. Subscribe so you don't miss our next deep dive into history's greatest puzzles, and definitely drop a comment telling us where you're listening from. Are you falling asleep in Tokyo? Driving through Texas? Doing dishes in Denmark? We genuinely want to know where our fellow history nerds are scattered across this planet our ancestors colonized. And as you drift off to sleep tonight or continue whatever brought you to this video, think about this. That naked skin you're in right now connects you to millions of years of human survival and triumph, to ancestors who crossed deserts and mountains, to survivors of climate disasters and ice ages, to innovators who mastered fire and invented clothing and built civilizations. You're not just a naked ape, you're the latest chapter in the most remarkable evolutionary story on Earth. Sleep well, fellow humans. We've earned it.